Hello, viewers. Do you know which is the most launched rocket engine in the world? It's SpaceX's Merlin engine. It is the core of the Falcon 9 rocket and has supported more than 550 launches, with the highest number of single reuse reaching 32. Today, we will take you to learn more about this engine that makes the cost of commercial spaceflight drop dramatically, and see what survival wisdom, technological breakthroughs, and once triggered a controversial tidbit behind it. The birth of the Merlin engine from the beginning of the Shoulder Life mission. 2002, when SpaceX was just established. The commercial space market was completely monopolized by Boeing, Lockheed Martin, and other traditional giants. At that time, the cost of a single launch could easily be hundreds of millions of dollars. For the startup company, the risk of bankruptcy if you are not careful. Musk founded SpaceX's goal is to reduce the cost of space exploration, to achieve Mars immigration, but the premise is that the company has to survive first. Therefore, the core of the design of the Merlin engine is minimalist structure, cost control. It does not pursue the ultimate performance, but to verify the feasibility of commercial spaceflight with the lowest technical risk. This liquid oxygen kerosene engine utilizes gas generator cycle technology, which is a very simplified structure. The turbopumps of conventional rocket engines are usually 2- or 3-axis designs with numerous and complex parts. The Merlin engine uses a single-axis turbopump, integrating the oxygen and fuel pumps on the same shaft and combining the induced wheel and impeller into one, eliminating the separate induced wheel component. This directly reduces the number of parts by more than 30%. This not only reduces manufacturing difficulty and saves costs, but also makes the engine run more stably, because the fewer parts, the lower the probability of failure. From the actual performance point of view, the reliability of the Merlin engine really cannot be said. Since the Falcon 9's first flight in 2010, it has successfully supported more than 550 rocket launches. As of January 2026, the total number of payloads successfully placed in orbit has exceeded 2,400 tons. In 2025 alone, Falcon 9 will complete 165 rocket launches and deploy more than 3,800 spacecraft annually, making it the world's most frequently launched launch vehicle power system. What is more amazing is that the Merlin engine also realized the first human rocket first-stage recovery reuse. Up to now, the Falcon 9 first-stage booster has completed 537 recoveries, including 32 flights of booster B1067, which is close to the design reuse target of 40 times. The multiple reuse of a single booster has allowed SpaceX to save nearly $900 million in launch costs. This reliability also allows the Falcon 9 in the commercial launch market to stand firm. Got a lot of orders for SpaceX's subsequent research and development of the accumulation of funds and technology base. Musk has publicly stated that the minimalist design of the Merlin engine is one of the keys to SpaceX's early survival. In fact, the Merlin engine didn't start out so mature. It went through 3 iterations, each one addressing the pain points of the previous generation. Let's look at it step by step. The first generation is Merlin 1A at that time. SpaceX's idea was to quickly verify the feasibility of the technology, so it used a simple structure of the ablative combustion chamber. This cooling method is through the wall of the combustion chamber wall. Material in the high-temperature gas scrubbing under the decomposition and gasification to take away the heat to protect the wall. The advantage of the R&D cycle is short, low cost, very suitable for startups. The Merlin 1A did help SpaceX validate the fundamentals of the liquid oxygen kerosene engine. However, the problems of the ablative design are also quickly exposed. First, it is disposable, and the thermal insulation material will be consumed and must be replaced after each launch, which is contrary to SpaceX's goal of reducing costs and realizing reuse. Second, the thickness of the wall will change during the ablation process, resulting in an unstable thrust output and affecting the attitude control of the rocket. More critically, the higher the combustion chamber pressure, the faster the ablative, the higher the pressure of the combustion chamber. the faster the consumption rate of the material, which limits the upper limit of the thrust. In actual tests, once the pressure exceeds the threshold, the material consumption is suddenly accelerated and even wall spalling occurs, which can have a serious impact on safety. As a result, the Merlin 1A was eliminated after only a few tests, and SpaceX quickly turned to regenerative cooling technology and successfully developed the Merlin 1C. The Merlin 1C was the first engine to be officially installed on the Falcon 9, and its core improvement was regenerative cooling. Simply put, this technology makes the fuel flow through the cooling channels on the wall of the combustion chamber before it enters the chamber, absorbing the heat from the wall before combustion. This solves the cooling problem and utilizes the heat absorbed by the fuel to improve combustion efficiency, and is a key technology to achieve reuse. At that time, to meet the challenge of the complexity of manufacturing conventional reducer nozzles, Merlin 1C used a spiral wound steel pipe nozzle. This design, similar to a woven rattan chair, was able to theoretically adapt flexibly to changes in nozzle diameter, eliminating the need for a complex hydroforming process. However, the spiral wound nozzle later led to big problems. First, there were problems with the high-temperature gas seal. The joint between the steel tube and the main body of the combustion chamber was difficult to seal, leading to leakage of the high-temperature, high-pressure gas, which not only affected thrust, but could also corrode other components. Second, torque interference also poses a challenge. The tiny torque generated when the nozzle works is not enough to make a large rocket like the Falcon 9 rotate significantly, but it will affect its attitude control accuracy, especially in a vacuum environment, and the impact on the upper stage rocket is more significant. In addition, the copper bushing plus nickel-cobalt alloy plating process used for the Merlin 1C has a week-long manufacturing cycle, which is unable to meet the demands of large-scale mass production. These problems forced SpaceX to continue to optimize the design, and eventually develop the Merlin 1D, the core model currently used by the Falcon 9. The Merlin 1D can be considered the ultimate mature version of the Merlin series, and its improvements all hit the nail on the head. First, it uses the chamber and jacket integrated design, the copper bushing and steel jacket directly welded together, completely solved the problem of high-temperature gas sealing. Not only significantly improved the sealing and reliability, but also simplify the manufacturing process. Next is the 5-hole pinhole nozzle design, which appears to be just 5 needle-like holes on the injector panel, but solves the major problems of fuel mixing and combustion stability. The working principle is, liquid oxygen is injected vertically from the center, and fuel is injected from the horizontal holes, the two in the center of the combustion chamber, to form a recirculation zone. The impact of each other to form turbulence, like shaking a martini glass, so that the fuel and oxidant fully mixed combustion. This mixing method may seem crude, but it's perfectly efficient and effective in avoiding combustion instability, a common problem with liquid rocket engines. Musk also said that the Merlin engine has never had a problem with combustion oscillation, which is very rare in liquid propulsion systems. In addition, the Merlin 1D incorporates injectors and a main fuel valve. Borrowing the principle of a lawn sprinkler, it automatically pops up and opens when there's enough pressure, and retracts and closes when there's not enough pressure. This further simplifies the structure. For the manufacturing process, the Merlin 1D abandoned inefficient plating in favor of a casting, forging plus machining process. Copper alloy combustion chamber blanks were made, cooling channels were machined, and the steel jacket was welded. As a result, the cycle time was reduced from a week to a few days. Costs were reduced, and the precision and consistency of the cooling channels were improved. In terms of performance, the Merlin 1D has a thrust of about 845 kilonewtons, 190,000 pounds, at sea level, and more than 934 kilonewtons in vacuum, with a thrust-to-weight ratio of 150:1, which is about a 30% increase in thrust compared to the Merlin 1C. A single Falcon 9 first-stage rocket carries 9 Merlin 1D engines. and the total thrust at liftoff exceeds the combined full power thrust of 5 Boeing 747s, enough to support all types of near-Earth orbit missions. In the first 11 days of January 2026, it completed 4 launches, successfully delivering 99 payloads into predefined orbits, demonstrating its formidable strength. The core strengths of the Merlin engine can be summarized in 3 points: minimalist structure, innovative nozzles, and efficient cooling. First, the single-shaft turbopump integrates the oxygen and fuel pumps on a single shaft, driven by a single turbine, and eliminates the independent induced wheel, thus dramatically reducing the number of parts and points of failure. In contrast, traditional rocket engines mostly use a 2-axis or 3-axis design, with many parts, complex structure, high cost, and high risk of failure. The Merlin engine, on the other hand, perfectly meets SpaceX's early survival needs by sacrificing some of the non-essential performance redundancy in exchange for higher reliability and lower cost. Next is the gas generator cycle. This cycle is simple. A small amount of fuel and oxidizer is drawn from the combustion chamber, burned in the gas generator, which drives the turbopumps, after which the gas is vented directly into the atmosphere. This design eliminates the need for complex reinjection piping and containment systems, resulting in a short development cycle and low cost. Although its energy utilization is lower than the substage combustion cycle, there will be a loss of some propellant energy. But for the early SpaceX, as long as it can ensure reliable launch and reuse, this energy loss is acceptable. This something-for-nothing design philosophy allows the Merlin engine to mature quickly with limited funding and technology. We have also mentioned the advantages of the 5-hole pinhole nozzle, which not only burns stably, but also supports deep throttling control, which is crucial for the recovery and reuse of the rocket. When a rocket returns to the atmosphere and lands, it needs to ensure a smooth landing by precisely regulating thrust. The Merlin engine realizes a wide range of thrust regulation by adjusting the supply pressure of fuel and oxidizer. During the actual recovery process, the Falcon 9 first stage starts the 3 engines to slow down, and then starts the central engine when approaching the landing platform to precisely control the attitude. And the whole process is very smooth. In addition, the simple structure and low manufacturing difficulty of the pinhole nozzle are suitable for mass production, laying the foundation for the mass production of Falcon 9. The upgrade of the regenerative cooling process is also very critical. From the plating process of Merlin 1C to the casting, forging plus machining process of Merlin 1D, not only the production efficiency has been improved and the manufacturing cost has been reduced, but also the reliability has been significantly improved. The electroplating process suffers from low efficiency, difficult to control the thickness of the coating, and is prone to porosity and defects, which affect the cooling effect. In contrast, the new process is able to produce high-precision copper alloy bushings that allow for more precise sizing and shaping of the cooling channels, resulting in more uniform cooling. As of 2026, Falcon 9 boosters equipped with this cooling system have been reused up to 32 times, which is a testament to the reliability of the process. Speaking of which, it is necessary to mention an event that once triggered widespread speculation: the Falcon 9's 45-degree deflection to the left on its maiden flight. On June 4, 2010, the first Falcon 9 rocket suddenly deflected to the left in the early stages of liftoff, with the maximum angle reaching 45 degrees. At the time, the ground control team was sweating. However, the rocket eventually entered its intended orbit without incident. The incident sparked widespread speculation. Among them, the 2 most popular theories are: one is due to the torque generated by the spiral winding nozzle, which led to the deflection. The other is due to the deviation in the angle of the gas generator's installation, which generated an additional rolling torque. But Musk later clarified in interviews that the real cause was an engine angle calibration error. During pre-launch ground tests, engineers used mechanical calibration to adjust the engine mounting angle to 0, i.e., the thrust direction was vertically upward. However, due to the precision limitations of the calibration equipment and subtle human error, the actual angle was not fully zeroed and there was a slight deviation. After the rocket is launched, a small horizontal component is created in the thrust direction. During the initial low-speed phase of takeoff, this horizontal component was amplified by aerodynamic forces, resulting in a significant deflection of the rocket to the left. Musk emphasized that this was a minor problem that was unavoidable in early development, not an engine design flaw. For the spiral nozzle torque and gas generator tilt, Musk has also explained, the torque generated by the spiral nozzle is very weak, not enough to drive more than 300 tons of Falcon 9. The Falcon 9 is not strong enough to deflect significantly. This torque will at most cause a slight disturbance to the upper stage rocket in a vacuum environment, while the effect on the first stage rocket in the takeoff phase is negligible. In addition, the gas generator is mounted at a tightly calibrated angle that is not tilted, and the resulting torque is precisely calculated not to interfere with the rocket's attitude. SpaceX later optimized the calibration process with more sophisticated laser calibration equipment, which solved the problem completely. As of January 2026, the Falcon 9 has achieved hundreds of consecutive attitude-stabilized launches without a similar deflection anomaly. We can also see SpaceX's early technical rigor in this case. Immediately after the problem on the first flight, they set up a special team to analyze the flight data and reconduct the ground test, and quickly locked down the course and made improvements. This ability to respond quickly and solve problems is also an important reason why SpaceX can stand out in the commercial spaceflight competition. Through this incident, the outside world also gained a better understanding of the design features of the Merlin engine and dispelled misconceptions about spiral wound nozzles, which earned the Merlin engine more recognition. It is worth mentioning that this incident did not affect the commercial orders of Falcon 9. SpaceX has shown a transparent and responsible attitude by disclosing the cause of the problem and improvement measures in a timely manner, thus winning the trust of customers. After talking about the Merlin engine, you may wonder, what is the difference between it and the Raptor engine developed by SpaceX later? In fact, these two engines represent the core technologies of SpaceX at different stages of development, and their design goals and application scenarios are completely different. The Merlin engine takes a minimalist and practical route, applicable to Falcon 9's near-Earth orbit mission and recovery and reuse, while the Raptor engine takes an extremely efficient route, used to support interstellar voyages of Starship rockets. The relationship between the two is one of complementarity, not substitution. The most central difference between the two lies in the cycle method. The Merlin engine uses a gas generator cycle, a cycle that is simple in structure, low in cost, and short in development cycle, but low in energy utilization, with part of the propellant being burned and then discharged directly into the atmosphere, unable to participate in the main combustion zone to do work. The Raptor uses a full-flow graded combustion cycle, which is currently one of the most advanced rocket engine cycle. It burns oxidizer and fuel into separate gas generators, and the resulting gas drives the oxygen and fuel pump turbines. The turbine exhaust is all injected back into the main combustion zone for combustion. This way to maximize the use of propellant energy, with better thrust and specific impulse performance. But its structure is very complex, requiring two sets of independent gas generators and turbine pump system, the number of pots used far more than the Merlin, resulting in the development of the difficulty and cost of a substantial increase. In addition, the turbopump structure is also different. Merlin uses a single-shaft, single-turbine design that integrates the oxygen and fuel pumps on a single shaft, driven by a single turbine. This design combines the induction wheel and the impeller into a single unit, which is very simple and reduces the number of failure points. But at the same time it also limits the thrust ceiling and efficiency. The Raptor, on the other hand, utilizes a two-axis, two-turbine structure, with the oxygen and fuel pumps driven by separate turbines, creating two separate drive systems. This design enables more precise control of the mixing ratio of oxidizer and fuel, thus improving combustion efficiency. In addition, the Raptor's turbopumps use more advanced materials and manufacturing processes to withstand higher temperatures and pressures and to meet the demands of high pressure, high flow conditions, thus further enhancing performance. The choice of propellant also reflects the needs of different application scenarios. Merlin uses liquid oxygen kerosene log as propellant, which is low cost, easy to obtain and moderately difficult to store, making it ideal for large-scale application in NEO missions. In addition, liquid oxygen kerosene is relatively simple to maintain and is suitable for recycling. Raptor uses liquid oxygen methane as propellant, which has a higher energy density and cleaner combustion products that do not produce residual pollutants, which makes engine reuse and maintenance more convenient. What's more, methane can be synthesized on Mars from carbon dioxide and water, which is critical for Starfleet's mission to Mars. It would allow Starship to synthesize fuel in situ on Mars, thus enabling self-sufficiency on interstellar voyages. However, liquid oxygen methane is more difficult to store and more expensive to manufacture, and developing a liquid oxygen methane engine would also require solving a number of challenges such as low-temperature storage and combustion stability. In terms of design goals, Merlin's core is to achieve reliable launch and recovery reuse at the lowest possible cost in order to validate the viability of commercial spaceflight. As a result, the design is centered around simplicity, reliability, and low cost, and therefore sacrifices some performance redundancy. The core of the Raptor is the pursuit of extreme thrust, efficiency, and reusability to support the Starship to complete interplanetary missions to the Moon, Mars, and other interplanetary missions. With the success of SpaceX in the commercial space market through the Falcon 9 and accumulated enough funds and technology, its strategic goals began to shift to long-term interplanetary exploration. Raptor design is also towards a more efficient direction. In terms of performance parameters, there are also significant differences between the two. The Merlin 1D has a thrust of about 845 kilonewtons at sea level, 934 kilonewtons in vacuum, and a thrust-to-weight ratio of 150:1, while the Raptor 2 has a thrust of 2,300 kilonewtons at sea level, more than 2,500 kilonewtons in vacuum, and a thrust-to-weight ratio of more than 200:1. The Raptor 2's thrust is more than 2.5 times that of the Merlin 1D, and has a much better specific impulse performance. The Raptor's reuse target is even higher, with dozens or even hundreds of reuses planned, far exceeding the Merlin's current record of 32. However, the increase in performance also brings an increase in complexity and cost. Raptor research and development cycle of more than 10 years. The investment is far more than Merlin. Manufacturing costs are also higher. It should be emphasized that the success of Merlin laid the foundation for the development of the Raptor, Falcon 9 through the Merlin to achieve the recovery of reuse, verification of the technical feasibility of rocket reuse, but also for the reuse of the Raptor design provides a reference. In addition, Merlin's regenerative cooling and thrust vector control technologies have also accumulated valuable experience for the development of Raptor. Meanwhile, the huge commercial launch revenues generated by Falcon 9 provide sufficient financial support for Raptor's long-term research and development. As of 2026, Falcon 9 will still undertake SpaceX's major commercial launch missions. During this period, Raptor will be in the Starship test iteration phase and progressing toward practicality. Together, the two will support SpaceX's near-Earth orbit missions and interstellar exploration. Around the Merlin engine popularization, SpaceX has also cooperated with the Avery Diastrant Channel to launch a series of derivative commercial products, thus forming a popularization plus commercial benign interaction. This has formed a benign interactive mode of science popularization plus commerce. This not only expands the influence of space science popularization, but also realizes the transformation of commercial value. Among them, the core derivative product is the 1:100 scale metal Falcon 9 model. This is the first rocket model launched by everyday astronaut, which is designed strictly in accordance with the appearance details of Falcon 9, including the Merlin engine layout, fairing shape, and arrow markings, etc., and strives to restore the shape of the real rocket. The model is made of high-quality metal materials and undergoes precision machining and surface treatment, with high fineness and durability, making it ideal for space enthusiasts to collect and display. According to public information in the space model market, the price of similar Falcon Y models is about €8 for the A scale version and €87.5 for the 1:200 scale 3D printed version. Popular product in the collector's field degree of reproduction and material advantages. This model is not only a mere commodity, but also an extension of space science popularization. Through the physical model, people can more intuitively understand the structure of the Falcon 9 and the layout of the Merlin engine, thus enhancing the fun and interactivity of science popularization. Priced to strike a balance between collector's value and mass purchasing power. The target audience includes space enthusiasts, students, and collectors. Consumers can purchase the model through the official mall everydayastronaut.com, which also provides detailed product descriptions and instructions for use, reflecting the spirit of professional service. In addition to model rockets, Everyday Astronaut has also launched a series of aerospace-themed peripheral products, such as RD-171 rocket-themed t-shirts and small aerospace patterned apparel, etc., which combine aerospace elements with daily necessities in a simple and fashionable design. These products not only meet the personalized needs of space enthusiasts, but also attract more people to participate in science popularization activities. For example, the RD-171 themed t-shirt is printed with a structure diagram and related text of this classic Russian rocket engine, which is both popularizing and ornamental. The small aerospace patterned apparel combines the elements of satellites, rockets, and planets into its design, which is suitable for daily wear and brings the space culture closer to life. These peripheral products are sold through the mall of everydayastronaut.com, which builds a business closed loop of science popularization content plus physical products. The Science Plus business model not only brings additional income to Everyday Astronaut, but also enhances the interaction between the channel and its viewers. The viewers support the science content by purchasing peripherals, while the channel can use the revenue to produce higher quality science videos, thus creating a virtuous cycle. In addition, the dissemination of peripheral products has also helped more people understand SpaceX's space technology and exploration concept. For example, when someone buys a model of Falcon 9, he will introduce the knowledge of Falcon 9 and Merlin engine to the people around him, which indirectly promotes the popularization of space science. This indirectly promotes the dissemination of aerospace science. As the frequency of Falcon 9 launches increases and the public's interest in space exploration grows, the market demand for this kind of peripheral products continues to grow, further verifying the feasibility of this model. In terms of content planning, Everyday Astronaut has also clearly predicted that the next installment will be an in-depth analysis of the Raptor 2 engine, continuing the idea of the popularization series of space power systems. The video series takes the core engine of SpaceX as the starting point, from Merlin to Raptor, and gradually introduces the development history and principles of aerospace power technology in depth, forming a complete scientific and popularization vein. As an improved model of Raptor series, Raptor 2 has significant improvement in thrust, efficiency, and reusability, which is the core power of Starship and the focus of space enthusiasts. The next video will focus on the Raptor 2's technological improvements, performance parameters, development history, and application in Starship, further enriching the popularization of aerospace power systems. As a result of the latest developments, the Starship's test mission is progressing steadily. If all goes well, the first orbital test flight is expected to be realized in 2026. This makes the science content of Raptor 2 even more current and interesting. To ensure the professionalism and authority of the science content, Everyday Astronaut also invited members of the SpaceX core team, including Musk, to participate in interviews to ensure the authenticity and accuracy of the content. At the same time, the channel transforms the complex principles of space technology into easy-to-understand knowledge through animation demonstrations, physical displays, and on-site explanations, lowering the threshold of understanding. This professional yet vivid style of science popularization has won the channel a large number of fans, making it a globally renowned platform for aerospace science popularization. In the future, the channel will launch more high-quality popular science content centered on core themes such as Starship rockets and the Mars exploration program to further promote the popularization of space culture. With SpaceX's plan to complete 200 rocket launches by 2026, and the advancement of the Starship test flight mission, the related popular science content is expected to continue to gain a high level of attention, bringing more traffic and influence to the channel. In addition, the channel has established a fan-funded creative model by accepting financial support from viewers through the Patreon platform. Patreon supporters are able to access exclusive science content, behind-the-scenes footage, and privileges to interact with the creators, further enhancing a sense of engagement and belonging. This diversified business model provides a guarantee for the long-term and stable development of the channel, while ensuring the continuous output of popular space science content and contributing to the promotion of the global space industry. To summarize, the key to making the Merlin engine a landmark product in commercial spaceflight is that it precisely meets SpaceX's early survival needs. It achieved high reliability and low cost through minimalist design and solved technical pain points through continuous iteration. Ultimately, it supported the high-frequency launch and recovery reuse of Falcon 9, thereby significantly reducing the cost of commercial spaceflight. Its success has not only helped SpaceX gain a foothold in the commercial spaceflight market, but also accumulated funds, technology, and experience for the subsequent development of the Raptor engine and the interstellar exploration program. That's all for today's introduction of the Merlin engine. I believe you have a more comprehensive understanding of this legendary engine. If you like today's content, please remember to like, subscribe, and turn on the little bell. Do not miss the next issue of the Raptor 2 in-depth analysis. Feel free to share your thoughts in the comments section. For example, what do you think is the most outstanding technology of the Merlin engine? Or what questions do you have about commercial spaceflight? See you in the next issue.